X. All right. So let's have a look. So something like this. Now, if we've got this apparent weight stuff, let's talk about, you guys have done a good job, I think, of given the limited stuff that you've got of making these things work. But let's start to get a little more systematic here. When we move forward into future chapters, and we're going to deal with consolidating forces from all different angles, not just convenient ones that are act along the same line. What we're going to do is we're going to come up with what's called equations of motion. The equations of motion are just going to be Newton's law along the coordinate axes. That's essentially all it is. So we'll do things like this, assuming that all the interesting directions in our picture or our situation are horizontal and vertical, then we'll say something like the one equation of motion is going to be that the x component of the net force is going to equal the sum, and this will just be a bunch of stuff that we'll do. It's going to be the sum of all horizontal components. And that's just going to equal m times a sub x. We'll do the same thing for y also. And the way that we're going to, like in some cases, we're going to have some forces that are going to act neither horizontally nor vertically, and then we'll go back to the vector stuff that we explored earlier and just break those forces into x and y components, right? And just take, the x component would be a part of this sum, and then the y component would be a part of the y component of the net force. For us right now, it doesn't have to be that complicated, because for us right now, everything is going to be acting in the same direction. But I want you to get used to this process, right? So we don't really need to specify the direction here. That's a bad thing next to it. So the net force up here, for us, we don't really have to specify that it's going to be in the x or y direction. It's just the only direction that things are acting in, right? So whatever those forces are, when we add them up, they're going to equal ma though, right? Okay, so let's draw a free body diagram, because that's always going to be our first step, is going to be to draw a free body diagram. Later in the class, we're going to have to do what's called an orthogonalized free body diagram, where all of the forces are broken into their right components. But it'll be easier now. So in this case, everything's vertical, right? We got a person standing on a scale in an elevator. The scale reads 799. When the elevator begins to move upward, the scale reads a constant 938, right? So then we've drawn one like this before. If this is the object, what's one of the forces acting? Gravity. What direction? Down. Notice that I haven't even probably specified, I don't remember if I did or not, but when we draw free body diagrams, all of the forces are starting at the object and emanating from it, right? They're not pointing at it, they're always starting there and then pointing away, right? So we've got gravity pointing down, mg, and we've got a force pushing up, which is what? What do we call it? Normal force, okay, good. And that's the normal force. We can attach a number to that one. What is it?
799.
Oh,
938.
It'd be 938, wouldn't it? Right? When it's moving upward, the scale, which is measuring normal force, when it's accelerating upward, the scale is reading 938, right? So that's the normal force. Okay. What is the weight of the person, though?
799. Well,
Why is it, you're right, why is it 799?
Because
that's when they're saying
well,
stuff.
it'd be 799 times 98.
Okay, right here, Ian, say it.
They're like equal, like the normal force and
And the scale are equal in this situation where the person is standing in a stationary elevator, right? We didn't draw it, but technically we were actually relying on another free body diagram. This is the one where the elevator is accelerating, right? But the one where it was stationary just looked like this. Both the normal force and gravity were equal, right? Because because there was no acceleration. Agreed? Everybody, and does that statement make sense? If it's stationary, if it's not moving, then by Newton's law, we know that the net force has to be, or the acceleration and the net force would both have to be zero, wouldn't they? Right? Because they're connected. If there's an acceleration, a net acceleration, then there is going to be a net force, right? But if there is no acceleration, then there is zero net force. So before, when the elevator is stationary, we had mg was the weight pushing down, and the normal force pushing up was 799, right?
What about gravity?
That is gravity.
Is
Why would? Okay.
is the
No, I mean,
But you were saying we were trying to find the mass of the person.
well,
That different-
we will find the mass of the person, but what do we know from this situation right here? Let's look at the equation of motion, right? The equation of motion is that the net force, which is 0, equals that minus that, right?
wait, isn't it divided?
The mass, right, but we're looking at weight right now. I'm looking at forces. When we're drawing free body diagrams, and you gotta be real careful about this in physics. Does it make sense that you can't compare apples and oranges in the sense that we couldn't put any other kind of vector quantity in there? They'd all have to be forces, right? Does that make sense? Okay, because we're comparing forces, we might get those, we're gonna calculate those forces in different ways. Like today we'll talk about friction a little bit, how we calculate a friction force, remind ourselves how to do that. But once we calculate the forces, a free body diagram is only looking at all of the forces acting on an object, okay? So if we look at this one then, if we go back to this situation where the elevator is stationary, what's the equation of motion we get from that? Well, that's just telling us that the net force is going to be the sum of those vectors, right? Up is positive, so it's going to be 799 minus mg, and it has to equal what?
Mass times.
What's the net force? Which is, right, so it's 0, isn't it? Right? Because the acceleration is 0, okay? That equals 0, and so what's that tell us that mg is equal to then, if I solve for mg? 799. Okay, that helps us in two ways. For one thing, it helps us because is the weight going to change? No, the person's not physically changing. Their weight is going to be the same the whole time, right? So now we know that up here, the magnitude of that vector is 799, right? Same as it was there. But the other thing it helps us with is that it allows us to calculate the mass, right? So what would I do to calculate the mass? Yeah, divide by g, right? Which is just we know that's just a constant of 9.80, right? So m would just equal 799 divided by g, which is what? Somebody? Yeah, calculator there.
Would it be a positive or negative?
Mass is always positive.
81.53.
G, okay, good. Is g positive or negative? No.
It depends.
G is positive.
Oh yeah,
Right.
yeah, because yeah,
It's pushing
right.
you up.
Well, no, g is just the magnitude of gravity, right?
So
See what I'm saying? Like a weight is a negative force because it pushes down, but g is just the magnitude of the acceleration of gravity. Okay. So 799 divided by 9.8 is something.
81.53.
81 exactly.
Well, with.
It goes on and on. Okay, so it's going to be 81.53, etc. But we'll just keep that number in our calculator, right? That's our mass. Okay. It's that number without rounding it off. Okay, so then let's go back up to this equation of motion. Right now we're looking at, this was all the stuff that really just came from that first part, right? That allowed us to know that the weight is 799 and to calculate the mass of the person. So now let's go back up to here. Let's look at this free body diagram. What's going to be the net force this time? What minus what?
939
Minus 799. Oops. Okay, which is what? 139. So then we know that MA equals 139, right? And those are newtons, right? If we did keep track of units. But once again, we're just gonna use standard units, so we can ignore the units. What do I have to do to solve for acceleration? Divide by mass. Okay, so if I divide both sides by m, which is just, the 81 number, right? Right there. Then we get an answer. We get the answer acceleration equals what?
1.704.
Okay.
Or I guess 1.70. 1.7.
Okay, but that's not even what we're looking for. So we're gonna leave that one in the calculator also. But we get a number like 1.7 what?
04.
04 blah blah blah.
Yeah.
It's in the calculator, right? But that is our acceleration. Okay, now what are we answering? How much time would it take for the elevator to reach a speed of 2.5 meters per second? Yeah, this is just kinematics now, right? So this goes back to that other stuff, previous chapter, where you became relative experts in kinematics, right? We just got to write down, here are our kinematic equations
Relative to who?
relative to where you were at the start of the year. Say it again. I better be, because this is gold. Yeah, yeah. Okay.
Straight fire right here. Oh yeah.
So let's see. Let me just.
You know what, Scott?
Okay, so let's go to the next page and do the kinematics.
I know the rules. Yeah, he does. He goes all in. He goes nuts. He's got fast enough.
All right, here we go. Here we go. Back to business. So let's make a list of stuff that we know then. So we know that the acceleration, we just calculated it, and it's about 1.704 blah blah blah, and that's in the calculator, right? What else do we know?
You need to find final velocity is 2.5.
Okay, will somebody raise a hand? Right there.
Gravity equals nothing.
We what? What do we do? What do we know? We don't need that one.
We know.
Okay, we do know it though.
Yeah.
Yes, Peyton had her hand up next. It was almost a split. Say it again. Final velocity. Final velocity is what? 2.5. What else do we know? Yes, sir. Initial velocity is what?
0.
0. Good. And what are we trying to find?
T.
T. Well, we got enough information now, right? What equation do we use?
Fat.
Number
2.
Velocity equals.
Yeah. Right? So can we cancel any terms right away?
Yeah, V naught.
V naught 0,
B nuts not.
and we're solving for T, right?
Kinematics.
Came from the board.
Right there. So if we solve for T, then T is just V final divided by A, which is 2.5 divided by that number,
Oh yeah.
which is rounded to how many sig figs? Looks like 2 is what?
1.5.
1.5. Isn't that cool? Now, that's pretty cool. You could do that problem now. You're doing something real.
Now, if
some
we're
real
ever on an
physics.
elevator, someone's like, "Oh crap, how long is it gonna take?"
Exactly. Now you'll be able to tell them.
But I think it'll take longer than 1.5 seconds to figure that out.
It will.
No, it's all about the mental math.
Okay,
It's
so-
all about. I'm so proud of myself.
Okay, questions? Questions? Is that making sense? Okay. What do you mean?
Like friction in the car.
Wind resistance.
Well, okay,
Actually, no. Actually, it's bypassing all that stuff because it's just telling us the actual acceleration that is happening. So the friction stuff is already taken into consideration. Realistic.
I mean, if we know, I'll answer that question. If we know that the scale is reading 799 the whole time, then that would be the exact answer, actually.
Yeah.
Okay. All right. Next issue. Okay, so this is, I don't think I would do that one. This is, we could do this, let's just talk about it for a second strategically. So do you see that this is very similar to the first problem, right?
It's going down.
It's going down, and what's it doing? It's going down, descends at a constant speed, the elevator slows to a stop at the bottom. So it's going down and doing what? Slowing down. Okay, so then, notice that that makes sense, doesn't it? That the scale's gonna read more. It's gonna read a bigger weight because the invisible hand is pushing you up, right? So the net force should be acting up, okay? So this is very similar to the last one. We could figure out what the mass of the person was and ultimately what the acceleration of the person was, right? Using a free body diagram, the net force equation. But then once we get that, this just devolves to another kinematics problem, doesn't it?
Which one would you be?
So if we look at the kinematics part,
Which one would you?
well, we'll look here in a second. Okay, so it's a kinematics problem. We will be calculating A, right? So A is going to equal some number. We don't know, but that's what you'll find. What else do we know here?
We know your
Yeah, what's final velocity? Zero. Good. What else do we know? Time equals 1.4. And what are we trying to find? Yeah, V naught, right? That's, oops, not zero. It equals question mark. That's what we're looking for. So it's almost the same problem. It's the same equation, isn't it?
Is this a related rates problem?
Okay, another one. Length of a pendulum. Very simple, but we haven't done any of these yet, so let's do one. Okay, so here's the pendulum equation for a simple pendulum, which is what we're considering. There's nothing complex. Now, it's not going to be a compound pendulum or a physical pendulum. It's just a simple pendulum, which is a massless string and a point mass at the bottom. Nothing in the world is like that exactly, but a lot of things are approximated by that. So here's the equation we use, right? The only equation we've got for a pendulum. What does T stand for? No. Well, I mean, period,
Yeah.
which is a time. It's the time for one complete swing, right? Back to the, does that make sense?
I mean, technically it is time.
It's
measured in time.
Okay, what's, hey, listen, hey guys, listen, this isn't gonna work for me today. We got too much to get through. We gotta, our wittiness is gonna have to be, we're gonna have to, I'm sorry, I love the wittiness, but today it's not gonna work. So what's L stand for? Length of the pendulum. G is acceleration of gravity. So if we're just trying to find the length of the pendulum, what do? What's our math look like?
You gotta do your PEMDAS backwards.
Okay. We got a reverse PEMDAS. We're gonna solve for L, which means, what do we do first to get the L by itself? Yeah, we're gonna divide by 2 pi, aren't we? Divide both sides by 2 pi. So we're gonna get T over 2 pi equals square root of LG. Now what?
Square it.
Square it. Good, square both sides. So we're gonna get T squared over 4 pi squared. And you could even just, if you want to, just put that in parentheses and square the whole thing. It's fine. You don't have to distribute. Let's do that.
Why do we go to 4 pi squared?
Because we squared.
Because I squared the whole thing, but we don't even have to. Yeah, we could just do this.
Yeah.
As long as you put it in your calculator carefully, just do it like that. That's fine. And then that's going to equal L over G, last step, multiply by G. Right? And so that's what we end up with. And now all we do is plug and chug. And it's really no big deal, right? We just put that all in our calculator. Okay? I won't even do that. You guys, that's no big deal. You guys don't do that. Okay? This is, well, let's just talk about this one for a second. It won't take long. So if we start with our pendulum equation, this time, what are we given? Given the period and the length, and what are we doing? Solving for G. I mean, same kind of thing though, right? All we're gonna do is just isolate G algebraically, and then plug and chug. How would we isolate G algebraically there? What could we do?
Yeah, we do all the original steps I did, but when We get to L over G, do we divide?
Yeah,
by
do
L?
the same thing.
Okay, so let's maybe take just a quick look at the algebra here. So we're gonna do the same stuff as before, we'll divide by 2 pi, right? So we get t over 2 pi equals the square root of L over G. And it doesn't really matter when you do this, but what do you suppose, well, I wanna solve for G. What's inconvenient about where the G is?
It's on the bottom.
It's on the bottom, right? So we got a couple choices. We could square both sides first, and that's fine, but then all we've really gotta do is just take the reciprocal of both sides, because that is a legitimate thing. It's okay to do that. If I do it to both sides of an equation, then it's still an equation, isn't it? Right? So we can invert both sides of an equation and then we get a different equation, but it's the one that we want, right? For example, if we said 1 over 4 equals 2 over 8, if I flip both sides, it's got to still be, right? These are the same thing, right? I'm just going to get 8 over 2 equals 4 over 1. It's a different equation, but it's still an equation. I have different values on each side, right? Does that make sense? So we could just either now or after we square both sides, flip both sides, or I could even just cross multiply. There's a lot of things I could do, but I got to get the G on top.
Cross multiply through the.
You can't do that.
Okay.
Not unless you split it into, okay, I'm gonna go one step further so I can answer that question. If I square both sides, I'm gonna get t over 2 pi squared equals L over G, right? And so if I distribute the squared, so I square the top and square the bottom, then I could cross
Can't we
multiply.
just divide both of them by L?
Because then I got, what do you mean?
Why not just divide both sides by
Well, I could, but then I'm still gonna have to invert then, right?
Why?
Because if you
I'm
solve,
solving for G, it's gotta be on the top.
yeah, but if
That'd
you
be one of
solve for,
But if you divide by,
yeah, if you solve for that
One,
number on the left, and then you just divide by L, that's G,
Yeah,
right?
could you
Yeah.
just like reciprocate both sides, just like.
You
turn both
can,
around
see
the
that's
side?
the reciprocal of G.
Okay, why not
Because,
do that?
I'll show you, because if I divide both sides by L, dividing by L is the same thing as multiplying by 1 over L, right? So that's gonna give me, if I do that, I'm just gonna get
oh, yeah, I see what you're
that,
saying.
right? Now on this side, I've got 1 over G. So if I just take that and flip it, so the L's on top, then it's
Yeah,
fine,
flip it, by the way.
okay?
Okay.
Right?
Doesn't matter which way you do it.
You still
Doesn't make any difference, you get the same answer either way.
So you just need to have it on the top.
Yep.
Basically,
That's
alright.
it, yep. Okay.
Physics.
Okay, here's what I wanted to make sure I got to was a friction question. Okay, so what about something like this? You're driving a 2,267 kilogram car at a constant speed of 10.9 meters per second along A, should be,
Turn, and then you get T-bone, you smash it.
along a straight icy road. Okay, you slam on the brakes and your wheels lock. You slide to a halt in a distance of 43.6 meters. We want to know, oh, cut that off. I think we're just looking for the coefficient of friction, but let me make sure. Oh,
Not too big.
Oh, it was that one, wasn't it?
which one was it?
I think it was that last one.
No, it's a little different.
Oh, okay.
It's, oh yeah, okay, so that's it. So we're just trying to figure out what's the coefficient of friction between our tires and the icy road, okay? All right, so we need the friction equation. For what kind of friction are we talking about here?
Rolling.
No.
Sliding.
Okay, sliding friction, is that static or kinetic? It's kinetic, right? Now, don't get these confused, because sometimes people think that this happens all the time. When you lock your brakes up in the car, your tires aren't spinning, so people think, oh, they're not moving, so it's static. But what you're really worried about is when you're talking about friction, remember that you're referring to the surfaces that are involved in that are creating the frictional force. And the rubber on the tire is actually sliding over the surface of the ice, and so it's kinetic, right? Static friction would be, an example would be like if you have a parked car with the emergency brake on, and you push against it, and it doesn't go anywhere. The reason it's not going anywhere is because it's pushing against you with a static frictional force, right? Because the wheels are not sliding on the pavement. Make sense? Okay. So then we need
But as soon as they did start sliding, would
Then
that
it would-
be kinetic?
Then it would be kinetic.
Oh.
So then, we've got a situation of kinetic friction, so we're gonna use the kinetic friction equation, so let's write that down. So we're gonna put a subscript of K by the friction F, right? And that's always equal to, what do we call this thing? What's that? What is it again? Coefficient of friction, very good. Coefficient of friction, that's just a number that you'd find in a table in a book somewhere, or Google it, you'll find it online. The coefficient, and it's gonna be a property of the two materials that are sliding. So in this case, it would be something like butyl rubber on ice at whatever the temperature of the ice was, because the coefficient of friction of ice even changes with temperature a little bit. So times normal force, right? Okay, everybody agree? So now this is a little harder question, because this time we're actually going to start to kind of sneak in a little look at dynamics in 2 dimensions. It's not really a big deal because one of the dimensions isn't really involved in the motion, right? The car's only sliding horizontally. So if we drew a picture of the car, we don't need a picture, we'll just do a free body diagram. What are the forces acting on the car?
Frictional force.
Okay, so if the car is moving, let's just say the car is moving in that direction. In what direction would the friction always be acting?
Against it.
Against it, right? So the friction's acting in that direction. So there's the frictional force. What other forces are acting? It's good that we're getting that on tape. That's good. So what are the other forces acting? Gravity, right? You got the weight of the car. And what else? I heard it somewhere. What's the other one?
The normal.
The normal force.
Yeah, normal force. Cleared up the brains.
Yeah, no, it's, yeah.
Gears are grinding.
Okay, so even though it wasn't, the chapter isn't really designed for you guys to think about it in 2 dimensions like this, you're ready. I mean, it's not a big deal. If we break this up into vertical motion and horizontal motion, this is a good way to kind of illustrate what I was talking about earlier, right? So what is the net horizontal force here? How many forces are acting horizontally? One, right? So horizontally speaking, the x component of the net force is one thing, and it's going to be acting backwards, right? And it's going to be frictional force. So it's just minus the kinetic frictional force, and that's going to equal ma, right? And being as all the motion is horizontal, we don't even have to say a sub x. It's just the acceleration, right? Now let's look at the vertical situation. So vertically, we've got these 2 forces acting, right? So the net force acting in the y direction, which is the vertical direction, there's 2 forces acting. What are they? What's the positive one? Normal force. Minus gravity. And what is the net force vertically? 0. Okay, that's right. Prove it. Nathan, well, how can you prove to me that it's 0? Because if it weren't 0, what would be happening to the car? Say it again. The acceleration vertically is 0. Good, because if the net force vertically weren't 0, the car would either be spontaneously accelerating upward off the ground or burrowing into the ground at an increasing speed. Neither of which happens, hopefully, right? So,
That'd be a phenomenal.
okay, so tell me though, that was an important equation though, wasn't it, Ian? That was an important equation because it allows us to do what? And really, we don't care about this part so much, but that part was important. Because what does it tell us? We need to know normal force, don't we, to calculate frictional force? Well, this allows us to calculate it because we're given the mass of the car, right?
And we have gravity.
And we have gravity, of course, right? So normal force then is just going to equal mg, which is, what was it, 2267 times 9.80, which is what? Somebody. 22,216.
Exactly.
Okay, that's exact, right? Okay, so that's our normal force, right? So now we can go back up here when we want to calculate the net force and therefore the acceleration. Actually, what are we trying to find here? We're just trying to find. Oh yeah, okay, right. We want to know what the coefficient is, right? Okay, in order to find out what the coefficient is, we would need to know acceleration, wouldn't we? Right? But we also need to know normal force. So let's take this equation now. I should have probably put that one on the bottom, but this is the equation we're working with now, right? So what does that tell us? We get minus frictional force, which is just going to be mu sub k, which is what we're looking for, times mu. That's a Greek m, I think. It's a mu. Times normal force is equal to ma, right? Okay, this is what we're looking for, isn't it? What's unknown? Let's circle all the unknowns in this equation. So that's an unknown, of course, because we're looking for it. We know that, don't we? So we'll underline knowns. That's known. What else is known? Is the acceleration known? Not yet, but it easily could be, right? Because look what they give us in the equation. They tell us a bunch of stuff. We could do a kinematics problem here and calculate acceleration, couldn't we? Right? So as a physicist, you're kind of thinking about this like, okay, I don't know the acceleration specifically yet, but I can find it. Right? That's stuff I can get at. This is where most of the problem is, but we're going to need to maybe fill in that blank from the kinematics information. So what are we given in this kinematics-wise? Okay, so the initial speed, right? Initial velocity is positive 10.9. What else do we know? But that's not a kinematic quantity. We know, okay, we know displacement, don't we? Is 43.6.
Is that the whole displacement?
Yeah, that's the whole displacement. So that's d minus d naught. D naught is just 0.
So that's all we need, right?
And then final velocity. Yeah, what's final velocity? Good. So we should be able to use that stuff and pretty easily solve for A, right? Okay, we could do it right there, couldn't we? Okay,
But we don't.
everybody agree? Oh, no, hang on, right here, sorry, right there, bottom one, there's no time. So we can use the bottom one, right? Everybody agree? Okay, how much time we got? Oh, good, we're gonna finish.
No, we
Let's
have
get
3
to it.
minutes.
We can do it.
But what about our thingadoo?
Yeah, we have.
Oh, yeah,
Oh, yeah,
stop
the
me,
thingadee.
stop me.
3 minutes.
I'll stop,
Okay.
I'll stop you. My alarm is set for 3 minutes from now.
Okay, good, okay.
Oh, you'll see.
You'll see.
Okay, so there's our kinematic stuff. I'm just gonna kind of go fast, just follow me here. So the last equation we're gonna use, v squared, and that's just speed. Final speed squared minus initial speed squared equals 2a delta d. We're solving for a, right? So we get a equals v squared minus v naught squared over 2 delta d, all stuff we know. The final velocity is 0, so we're going to get minus 10.9 squared over 2 times 43.6, which is what? 2.
I'm gonna say like.
43.6. I wanna say.
Well, tell me.
What?
I want it. I don't care what approximately. I want to know what is it.
Negative 1.3625. I believe.
Okay, and then
I'm gonna
more.
double
I'm
check
assuming.
that real quick.
You're keeping that number though, right?
Yes.
That seems reasonable. Okay, so then if we go back to this page, all we got to do here to solve for mu is divide both sides by normal force and plug in that number, right? And we got it. So mu sub k should equal ma over negative f sub n.
Be negative mu?
That's a negative, right?
We moved the negative.
We can move it to the top, doesn't
Oh,
matter.
yeah, because they're multiple, okay.
Well,
yeah,
but
yeah,
it's,
I see what you're
they're gonna
saying.
get negative over negative.
Yeah.
So that gives us M, which is 2267, times A, which is the 1.3 something number, right? It's in the calculator, divided by normal force, which is this number,
2216.
negative 22216.6. Throw that in your calculator, and what do we get?
Negative 0.139.
Okay, so, no, it should be positive.
Positive.
Should be positive because the acceleration is,
I put in, for the acceleration as negative.
okay, yeah, it should be,
Okay,
negative,
so-
right. Acceleration is negative, right?
Okay. Oh, I
Everybody
didn't have
agree?
the force.
From that page, it's negative?
Yeah.
Okay,
I
so
didn't have
then-
the force negative.
okay, so we're gonna get a positive answer then. Mu sub k is roughly equal to
139.
and how many sig figs can we keep? 3. So 139. Does that make sense? Does that seem like a reasonable coefficient of friction?
Yes.
It does, because think what the coefficient runs from. 0 is frictionless. 1 would be like the equivalent of a tire on concrete. And so, yeah, it's pretty low, right? Tire doesn't have much friction with the pavement. Okay,
All right.
man, that's a lot of physics.
Just in time, just in time. All right, what's the cool thing?